All right, well, we're back from our break again with a new tape. And as we were finishing, I just want to remind you again the idea of Gooey-Chapman-Stern, which pointed this out, and then which is now quite reproducibly noted by a number of experimenters, in that the concentration of ions, electrolyte ions, in the electrolyte solution can have an effect on the potential at the interface. As I said, this phi-2 effect, so-called phi-2 effect, is an important consideration when making electron transfer rate constant measurements, because what you see is that in order for an electron transfer to occur, we have to bring our molecule to the electrode surface, and that generally is going to be at basically the solvent radius away, a solvated ion radius away from the interface. At that point, the potential will be not the potential drop from the solution to the metal, but the potential drop from the phi-2 to the metal. And so the potential would be less than you would expect in that consideration. As we decrease the concentration of electrolyte, the phi-2 becomes even smaller, because more of the potential drop is now in the diffuse layer outside the electrode surface. The diffuse layer, depending on the concentration, can be not insubstantial. It can be from 10 to the minus 3. What do I have here? 10 to the minus, that's not right. 10 to the minus 3 centimeters to 10 nanometers in size. In other words, it can be quite extensive depending on the amount. Now, the very large diffuse double layer would be very low dilute concentrations. But if we go to even 1 millimolar concentrations, the diffuse double layer extends out 100 nanometers or so from the solution, from the electrode interface, and the phi-2 effect becomes easily noted. And so this is another reason why you would often prefer to use high concentrations of supporting electrolytes in solution, because at high concentrations the phi-2 effect will not be a problem in general, and it will be relatively constant. As we drop the concentration of our supporting electrolyte, now the potential at the interface is variable, and it varies with ion concentration, which is not ideal. The paper that I handed out for discussion next week has a discussion of some of these effects, and you'll be able to see some of the effects that changing concentration has. All right. Well, again, the GCS theory is a sort of an idealized interfacial region, and we had some pretty ideal electrochemical data to compare it to. But in many cases, the curves that we see with the in experimental conditions for, say, the surface tension versus potential are not really very close to an ideal parabolic shape. For example, although the shape for sodium fluoride is nicely parabolic, what we see is that the shape for ions like potassium iodide and potassium chloride, or sodium iodide and sodium chloride, are not parabolic. In fact, what you see is that the point of zero charge shifts a little bit, and this more positive side of the parabolic curve is actually shifted in a little bit, so we lose the symmetric shape of the thing. KF and sodium fluoride are both situations in which the fluoride ion and the potassium ion are not specifically adsorbed. So in those cases, because they're not really stuck to the electrode surface at any point, they actually give really good symmetrical curves like you'd expect. However, the iodide and the chloride now can be specifically adsorbed, and that causes the deviation you see at the positive side. as we go to more positive potentials, the more strongly adsorbed they are to the interfacial region. So usually cations, small alkali metal cations, are not a problem, but if we go to other sorts of cations that are often used, actually, it turns out that the opposite effect is seen. If we go to, say, KCl and compare that to a molecule that's tetraethyl ammonium chloride, tetraethyl ammonium chloride, TEACl would be an abbreviation for that. You notice again, the tetraethyl ammonium ion causes the, in this case now, the more negative side of the surface tension potential curve to be shifted. That suggests that now the potassium, because the potassium ion is not specifically adsorbed, but the tetraethyl ammonium ion is specifically adsorbed. It's stuck to the electrode surface. So we can think of it in this way. We've got now the outer Helmholtz plane with our ions like potassium ion, which is a small ion. It's got a solvation sheath of water molecules around it. It's got a layer of ion dipoles. In this case, solvent dipoles. The water is going to be stuck onto the negatively charged electrode surface. But then we can also have cations stuck to the surface. Now, we talked about anions being stuck to the surface, but now because tetraethyl ammonium is this large, physically large cation, it really has very little likelihood that there's going to be a significant amount of solvation around it. It's so big that there's not a lot of charge density to that ion. And so it's much more likely to directly attach to the molecule without this solvation sheath. And similar things happen in this case. Now, for negatively charged species, negatively charged electrodes, the chloride ions would not be specifically adsorbed, but if we went to a positively charged electrode, the chloride ions would also be there. So in this particular case, the anions would be out in solution. And the cations would also be, some would be specifically adsorbed, some would be non-specifically adsorbed, and then there would be a layer of water dipoles at the interface. Okay. Another thing that can happen when we have things adsorbed on the surface is if we have a neutral species. If we look at the electrocapillary curve for hydrogen chloride, HCl, or hydrochloric acid, if we put in some neutral molecule, such as, say, N-butanol, the electrocapillary curve becomes quite different. And right here at near the PZC, we see the curve sort of flattens out. And the idea here is that the butanol is adsorbed to the electrode interface, and that means that the capacitance is less than it would otherwise be at that particular point. Now, it turns out that because only near the PZC can the butanol really have enough energy to adsorb to the surface. In order to adsorb, it actually has to knock off some of the water dipoles on the surface. So at the PZC, and near the PZC, because there's very little charge on the metal, the dipoles are weakly bound to the surface, and so at that point, the butanol can actually get in there and stick to it, changing the surface tension. On the other hand, as we go to more positively charged or more negatively charged electrodes, the butanol can no longer really knock off those dipoles. They're much more strongly attracted to that surface under those conditions. Okay. think we'll just stop here for today for the notes, and then we'll continue tomorrow, next time, finish up chapter 12. And we have another set of notes that we'll also talk about that's related to chapter 12 too.